Hello, welcome back to Bike Forever. So this is a follow-up video to the previous one, which is the guitar tuner question mark assembly version, which itself was a video response to an 8-bit show and tell channel video of a similar name, which was focusing on basic optimizations using sound. So I'd sort of recommend you watch the previous video about this. But effectively what we're trying to do is use sound to measure the rate that the loop's running at in BASIC and then in assembler. So here we've got the here we've got the basic version of the code. And it's what the 8-bit show and tell channel Robin on there, his video got to the most optimized version of that. What I wanted to do today is improve on the way that I'm measuring the frequency. Yesterday I was using an Android phone with an app called Spectrum, and as good as that app is, and as good as it looks, it's got some inherent flaws, the biggest one of which is that it's measuring all the sound in the room, especially when you talk. It's measuring all the noise from the fans on the PC that's actually recording this video. If only we could just run the Commodore 64, which doesn't need a fan, obviously it's passively cooled, and it doesn't, to be fair, doesn't get that hot anyway. And also now I've got the oscilloscope, and I thought it'd be the ideal opportunity to use that to measure the frequency, and it turns out that that does a lot better job of measuring it. Anyway, the thing that was stopping me before was I was using a different connector on the oscilloscope, so it was just one that came with it actually, but so that's a BNC connector on the end of it for the oscilloscope, which is this. That's the BNC connector, and that just has crocodile clips on the other side, and this just is not the one I normally use to do anything with the oscilloscope. It probably introduces a fair bit of noise itself, so I've changed to just the standard probe. Problem is the tip of that won't connect to the center pin of the RCA connector, so I've just had to put this little sort of white cable with crocodile clips at both ends and connect to the ground to the outer part of that RCA connector. So if we run this now, which is run 10, just run this, and the benefit of doing it like this, you don't have to have the sound on. I mean, I can leave it on for a bit and then just mute it, so you don't have to listen to it. So that goes across the scope, and there's the display we get there. So on the scope, it's obviously set up for this, and it can sample at a much higher frequency, it can trigger, and it can measure everything basically about the signal. It doesn't matter really, but this is a 1 megahertz bandwidth scope at 1 gigasample a second, 2 channel. You could, the frequencies we're looking at here are obviously audio frequencies, so you could use in fact it probably would be better with an analog scope, to be fair, apart from the fact that this does measure the frequency directly. You could get into sort of measuring the time between this, you know, this is a square wave we're outputting. It's interesting to see actually, because the volume max there, if I just do a single sequence and freeze it, the volume max is on for a lot less than the volume off, which, looking at the basic code, you would think. See, it's doing this here. I think because this is the last part of the loop, poke 0, obviously these two you would think would be identical in time, although that is a floating point. Now, so poke 8, it's got to convert. Well, it's yeah, going to take longer than this poke dot supposedly, and you've got the go to dot, which is go to 0 as well in the 0 part of this. So I think that's why what we're seeing is roughly, well, we can sort of try and measure this using the cursors. So channel 1, and you can actually, this is why a scope is just amazing, really. It just gives you a window onto these things that you can't do this just with measuring things and doing it on your phone or an app on your phone. I know you can get these oscilloscopes, and they're not cheap, but they've come down in price a lot now. They're sort of not in the 500, 600, whatever pounds range. They actually come down a lot now, so nearer to sort of 150. You can get one even cheaper, to be fair, especially one that'll do audio frequencies. So measuring between start and end, and the DT there, it's probably going to be quite difficult to see on this. I'll take my word for it, that says 1.78 milliseconds. So that's the period of time it's on for. We can measure the period of time. It generally looks fairly consistent, the on and off time. So whoops, just overshot there. So 1.78 milliseconds it was on, and we just need to change the start. Whoops, it's moving start and end. Oh, great. Should have actually just pressed that button again. Just to move we've got to move the end back. Let's just do that. Get it on the line as close as we can. Nudge the start again back to there. So the off time is 2.66 milliseconds. So yeah, that's clearly off longer. And the frequency we're measuring is, or at least when this is on single sequence now and it's run stopped. So at that point it's 218.9. If we started again, it's varying a lot. It's varying between 218 and about 239 there. I think I saw the max. So yeah. Given those two numbers, the 1.78 milliseconds and 2.66, we could calculate the frequency fairly accurately. Obviously, it's jittering around quite a bit. It's probably just the thing, the Commodore 64. You know, there's other things happening in BASIC. So what I'll do now is load up the assembler version of this and see what we get with that. So what I'm going to do now is same measurement but with the Turbo Macro Pro loaded up, load the assembler program, and hopefully we'll get a good measurement. Now this is just a command because the file I've got this in is a .d64 file, and you have to open a channel to the drive and then pass a command to that drive, which effectively means just change directory or mount that disk file as the root directory. I wish there's a way around that. You can use fast load cartridges. I've got Action Replay in there, but fast load's not compatible with the SD2IEC, unfortunately. I don't want to use the Epic's fast load because the Action Replay actually does work for all the rest of its functionality, which is to actually freeze the program and recover, look at memory, do all the rest of it. So due to the way that this program's written at the moment, so I'll pause the recording while this loads. Take about 30 seconds. Right, so that's loaded. To run this, it's sys32768. That command causes it to execute machine code starting at that address. There we are in the Turbo Macro Pro assembler. So it's back arrow L, load file, and I think it's called SID best. So that's loaded now. So as per the previous video, I've not changed this, but yeah, just run through it quickly. Disable interrupts, load register A with 15, load register Y with 0, loop label, store register A in D418, which is setting volume to max, that's the SID chip address in hex, and then store register Y in the same address. So jump back to loop. So we can run that now. There's back arrow 3 to assemble it, S to start. There you can hear the tone. Again, I've got the thing connected so to the oscilloscope, so I can mute that. Don't need to listen to it. Can actually view it on the scope again. It's times like this where I wish I had a better camera. You can take screenshots actually on this, so I might do that. Press the auto set button because obviously it's a lot high frequency. So to measure, it's jumping all over the place. There's a lot of extra frequency components in here, but if you just do a single sequence, actually it's saying 89.9 kilohertz, which I don't really believe. I think that's because I see all these other bits in there. It's very difficult to measure this, to be fair. If we sort of play around with the trigger a little bit, get it a bit more stable. So to measure, see there it did. See, getting all this sort of thing in there, which is, it's not good. Can just tweak the settings a little bit. Might be able to get that. That's actually quite a clean. So now it's triangular rather than a square wave. We're actually measuring 281.6 kilohertz. So bearing in mind that this CPU on this is running at just under 1 megahertz, because it's a PAL version of the Commodore 64. 281.6 kilohertz. Yeah, that's just over a quarter of the CPU clock frequency, which I guess because it's such a tight loop in machine code, you'd kind of expect that. This measurement obviously is way beyond the measuring capabilities of the microphone on the Android phone. You're picking up harmonics of this in the previous one, so this is actually really interesting to see, and I'm quite surprised at that, but also in some ways, you know, not surprised that the oscilloscope is better. So yeah, there you go. That's we could just do the cursor measurement on this. So if we just go to measure, wait a minute, it is. There's the cursor button, and then time. So we can move. We'll just measure the period of one cycle. So if we do, that's just the start and then the end to that peak. So from peak to peak, we're seeing a DT, a delta in time of 11.05 microseconds. And actually the scope there, I don't know if you can see, you probably won't be able to see this on the camera unless I tilt this up. I should have done that before. It makes a bit clearer possibly. You've got 1 over dt, 1 over the delta time, the difference in time, so that's got 90.4 kilohertz, which is again different to the other measurements. But yeah, so depending on what you believe, 281 kilohertz or 90 kilohertz, I'm not sure, to be fair. Okay, just carrying on with this, what I've shown is what I think is the maximum speed that loop can run at, and I'm actually now considering that the 90.4 kilohertz was the correct frequency, just because when you looked at the scope, it's still running now, you're getting so many other sort of artifacts in there that really we had to do manual measurement on a single sequence between peak to peak with it triggered correctly, and that's where you get 90.4 kilohertz. Without doing the manual measurement, you're getting all those other frequency components. That's where the measurement there, 281. So it is actually varying between 90 and it's jumping all over the place. But yeah, in that position there, you can see. I think maybe because I've set this up and it's triggering better at the moment. So what I wanted to do is just change the code. Just to add like a artificial delay in there, see what the difference in timing is. So because this is running now, nothing that you do, the keyboard will do anything other than the reset button on the action replay. Press F3 to go normal reset. That prevents memory from being overwritten, so you can jump back into the assembler. Because yeah, the reset doesn't actually clear memory. What we want to do is just add a line in there. So we've got a max volume, min volume, and then we just want to, well, do anything. LDA. In fact, yeah, we could change it to the version which is going to be slower, which is LDA 15. I know what I've done here is optimise it as best I could, so I want to de-optimise this. I'm kind of doing this the wrong way around. LDA 0, and put that in the wrong place. LDA 15. Again, it's doing the same thing as was before, except it's doing it all in the loop. To delete a line, I believe it's back arrow delete. Yeah. Right, let's run that now. Get rid of all these other ones up here, all these lines. Probably I'll keep the disable interrupts, and then we'll see how much effect that has as well. So what we're going to do is back arrow 3 to assemble as before, and then it's S to start. So if I mute it and turn the volume up, can't really hear that. That's like actually a lot quieter. Let's just check that code again. So action replay, F3 normal reset, back in, set it to 0. Oh, right, obvious mistake. Yeah, I thought there was a bug. So not only are we optimising with sound, we're also debugging with sound as well. This is some crazy stuff. So yeah, I've got rid of the bug there. I had store register Y into that location. Because I hadn't pre-initialized them there, it was actually not using the value of register A. So we're going to do back arrow 3 to assemble again. Just press S to start. And you can hear the sound. You can sort of audibly hear it's slow. I've just muted it again because I want to measure this on the scope. So I was running. I shouldn't have pressed auto set there because I'd set it up. Single sequence. It's not too difficult to just readjust. Let's just single sequence it until we get it clean. So try and get the sort of true frequency of this, regardless of all the other noise. Go back to cursor in time and change the end point. So on this scope, change the. This is, by the way, if anyone wants an oscilloscope for a fairly reasonable price, it's as I said, I think I said before, it's 100 MHz bandwidth, 1 gig a sample a second. It's a Handtech DSO 510 2P. I find it's a really good scope. Okay, so we've got a measurement there. I hope you can see that DT is now 15.2 microseconds. It was 1.78, I believe. I'll have to check the video again. I'll probably put a caption up. And 1 over DT we're getting, so that the actual frequency, which is 1 over the time, is 65.7 kilohertz. So you can audibly and measuring it on the scope visually see that we've actually de-optimized the code. I'm going to go back in now and we're going to run the assembler again. See, we've got the SEI instruction, so we're going to comment that out so we're not disabling interrupts anymore. Assemble again. Let's just listen to the sound. That doesn't sound much different to me. But let's see what the scope says. Single sequence. Let it run. So we get a clean. As you can see here, it's not a clean frequency, and it's virtually identical in terms of the main underlying signal there. As you can see, it's more or less identical. Maybe a little bit different there. It might just be offset by amount. Single sequence again. It does. I think it does sound a bit different. Anyway, I think that's all for this video. I could carry on tweaking the code. So this video was intended to be optimizing code using sound. What we've actually done is we started off with the most optimized loop that I thought I could get, and then we've de-optimized it, but that's just for sort of educational purposes, I guess. Okay, that's pretty much it for this video. Put that on mute. That's pretty much it for this video. Thanks for watching. As always, like, comment and subscribe. Bye for now.